就给他们做。
你说的那个是我们地设系聘到的那个工读生嘛，就是帮我们就是接云签的工作。
哦，他弄得很好看，我看那个照片啊，每个老师都很帅，都这样。
对，他那个女生是真的很喜乐。
对，那个很可爱啊。
那个不是我的学生。
那不是你的学生。
你是登广告证吗？那个你以后可以吸收成你的下线。
可以啊，可以，他很可爱。他的工作是，他的工作就是我跟美少女不想吃的都帮我们负责吃。
哦，真的吗？他个性很好。
对。他说助教不想吃，他说那靠你，那我的也是。你调这样好吗？你这样把它放回去。头歪一点。头晕了，可以吗？
这样子可以。
这样很好，可以，可以。
我今天会比较短。
那就表示。
All right, so let's start. We are going to talk about magnetic materials starting from today. In this PowerPoint set, before we classify magnetic materials, we have to define what is induced magnetic dipoles. And we need to find a way to quantify such induced dipoles. And when we induce magnetic dipoles, those dipoles effectively generate new current sources. Okay, we also have to find a way to classify and quantify this induced current sources. So I will spend most of the time in the first subsection, static magnetic fields in materials. We need to find a way to properly formulate the materials using simple parameters. Okay? Now, if you still remember, in electric dipoles and in electric materials, we used epsilon r, the relative permittivity, to explain the material using a single quantity. In magnetic materials, we also want to find the relative analogy. So we use a relative permeability, right? So once we have a mathematical tool to describe magnetic materials, we then classify magnetic materials. Depending on the quantity of the relative permeability, we can classify the materials accordingly. And finally, we need to talk about the boundary conditions for magnetic materials as well, right? So as you can see, in the first subsection, we have lots and lots of titles, but essentially, we want to find how to quantify the induced magnetic dipoles, and the result of this dipoles will give a new term called magnetization current. And there are two types. One is the surface magnetization current. Another one is the volume. Okay? So we need to have proper mathematical formulations for both of them. And in the end, we will introduce a new vector field quantity called the magnetic field intensity. So in all textbooks, the magnetic field intensities would be described by using the capitalized H vector. Okay. So for this, I want to save for next Monday. So today we might be able to finish the top 3 topics, right? Okay, up front, how to create a current conducting closed loop. I mean, before today, in the examples, we just assumed we have a metallic wire, which forms a closed loop, but then we have a constant current flowing. But that's really superficial because, I mean, in the real world, without the battery, how can you generate a non-stop current, right? So that's not very practical. So if we look into the atomic sense, in a very microscopic view, the way to create a closed loop current conducting device, the magnetic dipole, is, well, if you have the nucleus and you have an electron orbiting the nucleus, the electron carries a negative charge, right? So in this case, if the electron is orbiting the nucleus in the clockwise direction, it's equivalent to a positive charge orbiting the nucleus in the counterclockwise direction, right? So if you have an orbiting electron, that is essentially identical to a closed loop with a constant current, right? So in a sense, if you have orbiting electron, or maybe the nucleus is spinning, but the nucleus is not ideal, completely uniform, then you form a very small closed loop current. And then you have the magnetic dipole, okay? So this is saying, well, if you apply external magnetic field, that magnetic field will force the electrons to orbit. Or if that external field forces the nucleus to spin by itself, these are the two potential ways to induce magnetic dipole moments, right? So in this case, with the presence of external magnetic field, the electrons start to orbit, so it is equivalent to a positive charge orbiting in a counterclockwise direction, and therefore, again, we use the right-hand rule. The positive charge is orbiting this way, so it's producing an induced magnetic dipole pointing upwards. So the definition of magnetic dipole is still the same. Basically, your magnetic dipole moment, which is a vector, is in the surface normal direction using the right-hand rule, and then you have the amount of current times the area. Right? So basically, if you have a magnetic dipole moment, the unit is amp times meter squared. Okay. Now, basically, usually a bulk material has no non-zero magnetic dipole moment without externally applied field. Okay, for typical materials. Of course, we have permanent magnets, but that's another story, right? So basically, for typical materials, you might be able to induce magnetic dipoles when you apply external field, just like the dielectrics, okay? All right, so now we introduce a new terminology, which is called the capitalized M factor, which is called the magnetization factor. It's very similar to polarization factor in dielectrics. So in magnetic materials, if you have the capability to induce magnetic dipole moments, we are only trying to count how many magnetic dipole moments are there within a very small value. Therefore, basically, the magnetization factor is just the sum of all the induced magnetic dipole moments within that small value. So it's a value density of the induced magnetization dipole moments. All right? Now the unit for N, capitalized N, is ampere per meter. Right? Because you have N divided by delta V. Delta V has a unit of meter cubed, right? So you divide this by meter cubed, then you have ampere per meter, right? So when you read the unit, this is like saying, well, this is more like a line current density, right? J, the current density, is how much current you have per unit area. But now you only have a meter in the denominator, so this is like a line current density, right? So this N multiplied by certain length will give you the unit of current. This is more like a line current density. Okay, so I'm not going into the details, but once we have the induced magnetic dipole moments in certain material, if all of this vector sum does not go to zero, remember, all the magnetic dipole moments are vectors, right? So you can have lots and lots of induced magnetic dipole moments, but if in the end, all the summations of the vectors go to zero, then it's not a magnetic material. But for a magnetic material, which means when you have externally applied field, and pretty much all the induced magnetic dipole moments would line up in the direction of your externally applied field, and therefore the vector sum is non-zero. Then you have a non-zero magnetization factor. So in this case, you have a magnetic material, right? Where you have a non-zero capitalized M factor. If that is the case, well, all we have to do is replace the current density in our previous Biot-Savart derivation, right? If you have some current loop, all the induced magnetic dipoles will sum up to form a current loop, right? So once you have a current loop, all you have to do is put into this formula, and then you have the resulting vector magnetic potential, right? So once you have a current conducting loop, it will produce magnetic potential and therefore the magnetic flux density. I don't want to go into the mathematical details, so if you want to know the math, please read section 6-6 in the textbook. It provides step-by-step derivations, but what I want to do is I want to extract the end result. But once you have a non-zero capitalized M factor, which means you are dealing with a magnetic material, in the end, once you have this magnetization vector, you will have the vector magnetic potential. But the N comes in two functions. One is, you notice the first term here is a value integration. It's a three-dimensional value integration, okay? And the second contribution is a closed surface integration. So this means if you have a non-zero n, if it performs curl operation, if it's still non-zero, then you have a contribution to the value. So this term, curl of n, is called basically the value magnetization current. On the other hand, n, a non-zero n, making a cross product to the surface normal, is called the surface magnetization current. Right? So the classification is very simple. Now you have a closed surface integration, and this term, if it's not zero, this contribution is called the surface term. And this is the value integration. If curl of n is not equal to zero, then you have a value magnetization current term. Right? So for the following slides, we are merely going to compare these terms with the electrical charge densities, and then we want to confirm these are indeed the right mathematical formulations. Okay? So if you still remember, for a dielectric material, once you have externally applied E field, you induce electric dipoles, and then you have the polarization vectors. The polarization vectors are denoted by capitalized P vectors. In electric materials, dielectrics, we also have the surface and the value charge densities, right? So if you still remember this, P dot the surface normal gives you the surface dipole charge densities, and the negative of divergence of P gives you the value charge densities. Now we move into the area of magnetism. We have a pretty similar result, but the only difference is now we have current densities instead of charge densities, right? So the surface magnetization current density is n, the magnetization vector, making a cross product with the surface normal. The value magnetization current density is the curl of the magnetization vector. Now, if you still remember, near the end of the previous part 1 set, I showed you it is actually very easy to convert from electricity to magnetism. All you have to do is change or interchange P by N and dot by cross, right? Look at it. If you understand E field very well, all you have to do is replace P by N and dot with cross, and then you have the result, right? So divergence, you replace it by current, right? So up to now, when you have induced magnetic dipole moments, in the end, if all the vector sum does not reach to zero, then you're dealing with a magnetic material. For magnetic materials, you have two potential sources of current densities. One is the surface, one is the value current densities. Okay? So in the following, let me explain. Let me try to qualitatively prove this is the right formulation for the surface magnetization current density, right? So here, I'm showing you a magnetic material. Your externally applied field is out of paper. And here we assume this is a nice magnetic material. So all the induced magnetic dipole moments, and therefore the resulting magnetization factor, is also aligned to your externally applied B field. Okay? So this is a well-behaved material. Now, if you look inside in a microscopic view, everywhere we would have orbiting electrons, right? And therefore, every place we can draw some small current conducting loops, right? Now, because all the magnetic dipole moments are aligned with your externally applied field, so all the currents are actually, well, in this case, counterclockwise, right? You follow the current direction using your four fingers, and your thumb points in the direction of your applied field. Okay. So everywhere you have a counterclockwise current conducting loop. So if you ask yourselves, well, if I am inside, for example, this point, right? Exactly at this point. Now this point is connected to two dipole loops. One is this one, another is this one, right? Exactly at the connection of this point. And then you ask yourselves, well, at this point, what is the net current? This is tricky because at this point, the left current conducting loop is giving an upward flowing current. But at this point, the contribution of the current from the right loop is pointing downwards, right? And assume this is a very uniform material, the amount of current for this loop is equal to the amount of current provided by this loop. So basically, at this point, the net current is completely canceled out. Okay? So this is the essence. If you have a very uniform magnetic material, you apply an external field, and everywhere you produce the same magnetic dipole moment strength, and they cancel out completely in terms of current. So where in this material do you expect to generate the effective current density? Everywhere inside, the currents are just canceled, okay, by different adjacent loops. So only at the surface, at the interface, where you have the ability to create magnetic dipoles, here inside the material and not outside, right? Here you have no magnetic dipoles, but here inside you do have them. So only at the surface would you anticipate to have non-zero current densities. So in this case, at the surface, you have two surfaces here. So you expect to have two surface magnetization current densities, right? Apparently, for the right surface, due to the flow direction of the currents, they are counterclockwise. So eventually, along the surface, you have a current flowing upwards. Okay? So let us check whether this cross product makes sense. And in this case, it's out of paper, right? So M is out of paper. And now for this surface, your surface normal pointing outwards is pointing to the right. So your N cross AN, right? N is into your eyes, cross AN is flowing upwards. At least, up to now, it agrees with our figure, and that formulation seems correct. What about this surface? Well, this surface, due to the current flowing direction, it would give you a downward flowing current density, right? But the mathematical formula is still the same. So in this case, M still pointing into your eyes, but now the surface normal is pointing to the left. So this N cross AN is now pointing downwards. So that is okay. We have double checked. This simple mathematical formulation holds, right? It holds. Of course, that is only a qualitative proof. So now we want to perform a more rigorous, more quantitative analysis, right? So let me give you a very small value. And inside this value, we do have a non-vanishing magnetization vector. And so in this small value, I do have lots and lots of magnetic dipole moments. And here I assumed I have current flowing in the counterclockwise direction, right? So if I have a counterclockwise flowing current, I produce a magnetization vector pointing in the x direction. So I'm using Cartesian coordinate x, y, and z, right? So the first thing is, well, how do you define its differential value? We're going to work from the definition, okay? So delta V is the differential value is placed in the denominator. So we have to find a way to formulate it. dx, dy, dz, well, we're working in Cartesian coordinate. And what is your magnetic dipole moment? Well, your magnetic dipole moment is nothing more than I times the area, right? So we only care about this surface area. Surface area is dy dz, right? But the direction is pointing in the x direction. So in the x direction, the amount of current times the area, dy dz. So now we put this into the definition. The definition of magnetization vector is the amount of total magnetic dipole moments divided by the differential value. So this is pointing in the x direction and having the amount of I divided by dx, right? As I mentioned, it has a unit of ampere per meter. This is like a line current density. So basically, from the analysis up to now, we can conclude we do have a surface current density, right? But looking at the figure, as we mentioned, JMS is more like a line current density. So this entire surface, right, this surface marked by the yellow, is flowing with the effective current density due to the existence of this magnetization vector, right? But this direction is obviously not in the x direction, but in the z direction, right? This is in the z direction. So how do we formulate this one? Basically, the line current density is I divided by the length in the x direction. Right? So this is I divided by dx, and in the z direction. So apparently, from your calculation of magnetization vector, the magnitude is identical to its line current density, but the direction, m is in the x direction, but your j is in the z direction. So apparently they don't match. But they will match once you perform the cross product of n to your surface normal. So the surface normal for this yellow marked surface is pointing in the y direction, right? So x cross y is equal to z, right? X plus y is equal to z, and you don't have a change in the magnitude. So this is a simple verification for that mathematical formulation, right? So once you induce magnetization vector, it produces the surface magnetization current density. Remember, its unit is ampere per meter, so it's more like a line current density. So this n cross an, this is a surface normal, is indeed a valid description, right? Okay, questions up to now? No? All right. So that is a very simple proof. It's not a rigorous mathematical proof, but it is drawing out some value, and you have non-zero magnetization vector, and you can do the confirmation, right? So we have checked. This is okay. This is valid. All right, so next question is, well, we dealt with the surface magnetization current density, and now we're looking into the value. Well, if you still remember, the volume magnetization current density is having the curl operation of M. First, you have to think, what is curl? Well, curl is trying to find the circulation, right? So therefore, you have to form a closed loop, and you find the net circulation. It is not zero, and you have an effective value magnetization current density. So the first question you have to ask is, when can this value be non-zero? In the current case, we have a very uniform magnetic material. Uniform means, well, homogeneous. Let me use a more correct term. A more precise term would be, what I'm trying to draw out now is a very homogeneous magnetic material. Homogeneous means each point in space gives you the same amount of magnetization vector. Right? Homogeneous means it's uniform in space, so all the results is not space dependent. So in this case, point by point, as we discussed, point by point, you have no net current. How can you expect the entire volume to show up with a net current? That doesn't make any sense, right? So if you perform the curl operation for this material, you don't even need to calculate it. It's zero. Because point by point inside, all the currents are canceled out by the adjacent loops. You don't even need to calculate. So when do you expect to have a non-zero value magnetization current density? When do you expect to have the curl of n to be non-zero? If this n vector is a constant, it's not spatially dependent, curl operation must be zero, right? What do I mean? If this n is some n0, a constant, curl operation performs differentiations in x, y, z, right? Constant gives you a zero differentiation, right? So the only possibility is, well, we are dealing with an inhomogeneous magnetic material. Inhomogeneous means, well, maybe for this loop, the magnetic dipole moment induced here is stronger as compared to this location, right? So even though the current directions are all the same in the counterclockwise direction to conform that your induced magnetic dipole moment is aligned to your externally applied field, but the magnitude can be different, right? So now you think, well, at this location, at this point, do you have a net current? You do, because, for example, for this one, it has a 5 unit of current flowing downwards. But from this green one, you only have 1 unit of current flowing upwards. So basically, you have 4 units of current flowing downwards. Now, in this case, you expect this entire value to show up as a current source. And that relies on the fact you have inhomogeneity, spatially non-uniform. Then you can have a bulk material giving you non-zero current. Okay? So that is the meaning of the curl operation. If this curl is not equal to 0, which means your material is inhomogeneous. Just like the case we discussed for the volume charge density for dielectrics, right? You need to have inhomogeneous material to give rise to a non-zero volume magnetization current density. Okay? So let's look at, well, a really inhomogeneous material in a microscopic sense. So over to the left, you have a stronger magnetic dipole producing material, and over to the right, you have a weaker one. So I'm using 3 current loops and 2 current loops to reflect that fact. So with the same externally applied magnetic field, the left one can give you 3 units of magnetic dipole moments, but over to the right, only 2. Now we form a closed loop, right? A surface. And we ask ourselves, what is the net current penetrating this closed surface area C? Well, we can write this. I define this location as x, and this is x plus dx, right? So I want to know the net current passing through this contour. So the Ix minus Ix plus dx, that is the net current. But as we all know, M, the magnetization vector, has a unit of ampere per meter. So all I have to do is m of x minus m of x plus dx. I'm evaluating the magnetization vector here and here. The difference multiplied by what? by this DC, by DC. That is equal to the net current, right? So the current density is basically I, the net current, divided by the surface area, right? Surface area is dz times dx. And I know the currents are in the y direction, right? Into the paper or out of paper, but in any case, it's in the y direction. We already know how to formulate the net current. Right? So in the end, the value current density is in the negative y direction, and this is basically the differentiation of n in the x direction, right? But remember, the n's, n of x and n of x plus dx are oriented in the z direction. So basically, you're performing partial differentiation of the z component of n with respect to x. This is not a simple derivation, okay? So it conforms to the curl operation, right? So this is not, again, not a very rigorous proof, but this shows you, once you see this formula, and if you're brave enough to understand, you need to have inhomogeneous material, meaning at this location and at this location, they actually give you different strength of magnetization factors. And you form the closed loop and you do the calculation by the definition, you can verify this is indeed true. This is a valid mathematical description to the induced value magnetization current density. Okay. All right, so that is checked. So time is well controlled. Let's take a look at one particular example. If I have a material, it's a cylinder-like material and it's magnetic. Since the geometry is cylindrical, of course, I want to use cylindrical coordinate system to describe it, right? So the textbook asks you, well, if this material molded in a cylinder is giving you a constant, well, if you look at this constant magnetization factor, you will be very happy. Why? Think about it. This material, the cylinder, is having a non-zero magnetization factor aligned in the z direction, but it's a constant. So everywhere, inside, everywhere, you have the same magnetization factor. Why would you be so happy? Because you know, in this case, you're dealing with a uniform material. Therefore, you don't even have to perform the curl operation, meaning this material does not give you a volume magnetization current density, right? You don't have the volume current density, and therefore you only have to care about the surface current density. You only have to care about the surface current density. But then the question is, how many surfaces do you have? For the cylinder, you have the top lid, so that is surface number 1. You have the bottom lid, the bottom surface. And then you have the third surface, that's the circumference, right? Now think about it. eventually, the surface magnetization current density is making the cross product with the surface normal. So in this case, N is aligned in the Z direction, right? So your N is in the Z direction, but your top surface normal and bottom surface normal both are also in the Z direction. So Z cross Z is equal to 0. Which means, in this case, even though you have surface number 1, surface number 2, and the third, the circumference surface, the top and bottom do not contribute to the surface current densities. You only have to take care of this surface pointing outwards everywhere. Okay? So basically, we perform N cross AN. In this case, the surface normal everywhere on this cylindrical surface is pointing in the radar direction. So you have a Z direction, M0 as a constant, making a cross product with AR. Z cross R is 5. So the resulting surface magnetization current density is pointing everywhere in the phi direction and with a magnitude of N0. So what does that mean? That means you can actually view the cylinder as lots and lots of current conducting loops with differential height of dz prime. So you have one loop here, another loop here, you increase the height of the loops. Okay? So this is equivalent to a huge current conducting loop with total height of F. But you can decompose them into lots and lots of small current loops, each with a height of dz prime. So why is that important? In the end, we want to know what is the total B field created by this magnetic material at an observation point of 0, 0, Z. Well, if you still remember, we actually analyzed a simple case, right? For a simple current conducting loop with current I, and our observation point is 0, 0, Z, same here. We already know the result. So if I have only one current loop, I know this is my end result from our previous example. So now the situation is we have lots and lots of this current conducting loops, but each one having a different distance to my observation point. So all I have to do is for each equivalent current conducting loop, I have this much amount of current, N0 times dz prime. That is the current conducted by this differential loop. Okay? And I have to take care of the proper distance from my observation point to its own Z location. And that's it. And then I integrate Z prime from 0, all the way to M. And that's it. Okay? So this is finding a real connection to your previous example, right? So once you have a uniform Z-oriented magnetization vector for a cylinder, you can view it as a series of differential current conducting loops, but each one is having a different Z value. So the end result is simple and straightforward, right? So again, a quick conclusion. Once you have magnetic materials you have the ability to create lots and lots of magnetic dipole moments. But if you have a uniform magnetic material, inside of it, you don't really have net current because the currents will be canceled out by adjacent loops. So you only have the surface current. In this case, you only have the surface current at the outer edge, right? So unless you have a non-uniform, have surface currents. Okay? So if you have the volume current density, that means your material is suffering from non-uniform in terms of space, right? All right, so let's conclude for the day. Next Monday, we are going to define the difference between B and H. So it's better for you to review the course contents before coming into class. All right, thank you. Let's stop here.